Magnetic force on a current-carrying wire. What if we have a wire with many charges flowing in one direction? This is called current. If this wire is placed in a magnetic field, all of the charges will feel a magnetic force. Let's derive an equation for the magnetic force on the wire. So let's start with the force on one charge. The magnetic force on one moving charge is given by this equation on the equation sheet. But what is velocity? Velocity is distance over time, right? The change in displacement over time. And then if we just rearrange this a little bit, take this time, put it under that Q there, what is Q divided by time? Q over T, charge per time, that's current. The force on one charge, this is from the previous slide, is Q over T times the displacement times the field strength times sine theta. Therefore, the force on all of the charges would be that same equation times n, the number of charges. If you take n and multiply it by Q, that is delta Q, the amount of charge per delta T. Therefore, delta Q over delta T is current, I. So I is current. L, this is how it looks on the AP equation sheet. So they have the curly L. L is the length of wire, B is the strength of the magnetic field, and theta is the angle that the wire makes with the field. A straight long wire carries an electric current to the left. The current is placed in a uniform magnetic field directed out of the page. What is the direction of the magnetic force on the current? Or you could think of it as being on the wire. Once again, we use the right-hand rule. So imagine there's just one charge in there going to the left. Use the right-hand rule the way you did before. Point the fingers of your right hand to the left, then point your palm towards you, away from the computer screen, and you can see your thumb points north, right? It points up towards the top of the page. So this wire might fly upwards. A 2-meter long wire carries a current of 3 amps east in a 0.25 Tesla magnetic field directed into the screen. What is the magnitude and direction of the magnetic force acting on the wire? First, to calculate the magnitude, we are going to use ILB. So ILB, and yes, there is a sine theta here. A lot of the times, though, sine is just going to be 90 degrees because they're perpendicular, right? Current is going to the right, whereas the field's going into the page. So this is like a 3D picture here, where this is like the z-axis, the y, and the x. They're perpendicular, so therefore sine 90 is just 1. So ILB. I is current, L is the length of the wire, which basically tells you how many charges are there in this wire, right? Because we have the amount of charge per second passing by any single location. We have the length of wire, which gives us kind of an amount of charges that are being influenced. There's forces being felt by them. And then we have B, the magnetic field. We see that the force on the wire, the force on all of the charges, is 1.5 newtons. And using the right-hand rule, we can determine that the force on the wire is this way. So once again, point the fingers of your right hand to the right, point your palm towards the computer screen, and your thumb points upwards.